So this was my test beam right here, and this was my first drawing, and this was the results of that, the displacement. So it was around 208.7 meters, or 8,217 inches. And we know that displacement is the distance that something has moved, or in this case would potentially move, is indicated by the program. And this part is predicted to move an impossible distance for it to still be on the wall. So we know that it's fallen off, it's down the stairs, it's so far gone, it's not even going to work at all. And we can already tell just by looking at the numbers that's going to fail without even looking at how it is bending on itself. And we know that displacement is due to the force that is put on it in newtons per the surface area, or just the amount of material that is the object. So if you have more force, less material, it's obviously going to impact it more. So in this case, adding more material and structuring it better would obviously help that. When we look at the strain, it's the amount of deformation an object undergoes due to the force being applied to it. And in this case, most of it is located in this top right corner, and it is fractional and dimensionless, so we can say just 7.96. But looking at the test, the place where the most strain is present, we already talked about that, it's in that top corner. And that is like in the red, it's at the max. If you scroll over it, actually in the program, it says, yeah, that is where like the most of it is. And so if we're just gonna recap that, it bends a lot there. It just bends. Stress is pretty similar to strain. It is the amount of force applied to a defined area. A defined area which can lead to permanent deformation. The max stress applied to the hook is once again in that previous corner with a force of 160 terapascals. A lot of our issues are occurring in the corner of the object, is what we're seeing. And a good way to fix that would be to add some more support there, so it spreads out the force and it's not just located in that one area. It's not just putting pressure on that hook, so it bends that bit in the corner. If we're looking at von Mises, it's a value that can tell you the object will yield or not. This is based off of whether or not the stress is greater than equal to the yield limit. If it is greater than or equal to the yield limit, it yields, obviously. In this case, where the stress was maxed out at 2.14 terapascals when the yield limit was 1.07 terapascals. So that number is bigger than the yield limit, it yielded. So for the redesign, I had like 6 different redesigns. Basically, it was on the theme of what is strong? Triangles are strong. Let's just add a bunch of triangles. So the previous test indicated that the hook's failure seemed to stem from the mass amounts of stress applied to the top of the corner by adding weight to the end of it. So that just put a lot of stress on the corner. By adding a rib to support the hook, or in this case, a bunch of them, it helps more evenly distribute the force applied to the object so it doesn't continue to put so much stress on that one place. Giving it a rib didn't help enough, as I mentioned, so I gave it a second one, 2 more holes or screws, and then for another design, I added a third and fourth rib because I wanted to see how much lower the displacement could get, and then I just kept adding. And yeah, it kind of turned out looking like a spider web. So the displacement, the difference between the two. This was really exciting for me because I felt like I got it down pretty low. I was like, okay, this is pretty awesome. The original displacement, we know it was like 8,217 inches, and then we got it down to 0.38 inches, which is kind of crazy. And since this was a huge improvement, you can see that not only can the hook actually hold the weight, it stays on the wall now. So that's awesome. You can see that it bends in a lot more places. And because it's bending and collapsing in on itself, it's actually taking the weight better because it's distributing it across the surface. And you can see everywhere it bends, that's where it's taking weight as opposed to just that one place. I have my videos here. And you can see that they play automatically, so they're just bending, they're showing the difference. You can see that the new design crumpled more than the first, and I was talking about that in the last slide. And you would think that goes, oh, that did a worse job, it gets crumpling and it's like falling and failing in itself, but it's actually, you can see visibly where it's taking the weight in all these different places as opposed to just this one spot. And so even though it crumpled, it maintained its position on the wall, and it could probably still hold the weight. The original stress was in terapascals. So when we're talking about the difference between the two stress, it went down to gigapascals, which that's like looking at feet to inches or meters to like millimeters now. Like that is a huge difference. So this is at massive changes, a terapascal is 1 trillion pascals, and a gigapascal is only 1 billion. So this new design was better suited to dealing with the 50 psi, or the 3.45 e to the 5th newtons per meter pressure, than the original. That's what you can see. The value of the strain also decreased dramatically, going from 7.6 to 0.0326, which led to less warping, as you can see. It kind of looks like it warps more, but when you're considering the fact that it's actually staying on the wall and bearing the weight as opposed to just falling off into the abyss, it's working a lot better. Because it's not warping as much, it's allowing it to bend, but to bear the load in a way that kept it on the wall. And what I learned from this assignment was, I learned that different designs can affect how forces interact with the object created. Some designs distribute weight and force better across the entirety of the object, and some don't have the capability to withstand force in certain places as well as a direct result of their design. In conclusion, by testing designs and reworking them as a result of these tests, you can produce a more functional end product. And that's it.